Oh. So yeah, hello everyone. My name's Artjom Joosen. I'm a machine learning scientist at Huawei and the first author of this paper. And so today I'll be presenting serverless cold starts and where to find them. So first, I just want to briefly discuss why we wrote this paper and what exactly is in it. So we're an industrial research lab, part of Huawei, and we work on improving Huawei's serverless cloud. And we do a lot of analysis internally, and we also work with academics. And in order to facilitate this collaboration, we've decided to open source the data and also a lot of our internal analysis. We've also written a previous paper 2 years ago that you may be familiar with. It also has a data release attached, and since then people have been asking, can we have multiple regions of serverless clusters? Can we have cold start data? Can we have event-based data? And now we actually do have all of those things. So yeah, now that we've released this new data set, the aim of this new paper is to highlight the especially promising parts of that new data set and hopefully move forward some of the underexplored areas in serverless. So first, I'll briefly go over function as a service. So that is a type of cloud product where developers write their application in terms of functions. Many people have already discussed this, but it's just here for completeness. And yeah, where exactly the function runs and scalability and so on, that's all handled by the cloud provider. And yeah, nowadays all major providers have this service. So you can imagine this as follows. A developer writes a function to do image classification. It can really be anything. It's given some arguments, some inputs, and it can be sent to the cloud to run in a pod. And at Huawei, all of our FAS offerings run on a platform called Yuanrong. So functions can be invoked by different types of triggers. For example, timers, storage events, or even other functions, like in a workflow pattern. So there are many types of these triggers. So functions are usually invoked many times, and traffic varies throughout the time of day. So actually, many pods end up being required to serve a given function, and there may even be millions or billions requests per day, depending on the function. So the number of pods has to be determined by the cloud provider according to demand for each function. And that's actually quite a non-trivial problem. And yeah, so that this is offloaded onto the cloud provider so that the end users and the developers do not have to worry about this. So when there aren't enough pods to serve all the requests, a new pod has to be added in what's called a cold start. But a cold start is actually many steps. And so a pod has to be allocated. We then have to deploy code into that pod. We then have to deploy any dependencies if we have them, and any scheduling and network overheads also have to occur. So it's actually a sequence of many steps. So yeah, cold starts are obviously slowing down our system, and we want to avoid them as much as possible. And many papers have written about how to reduce cold starts, but few of them actually discuss how, like, which functions cause these cold starts and which factors, which components in our system increase the length of a cold start. And that's mainly because there's no open source data sets to help researchers answer these questions. So just to clarify again, like what kind of data we are working with. So if we have a pod and a user sends a request there, that request is obviously logged, but in previous data sets, including our own older data set, what would happen is that you have a timestamp like 6:35 p.m. and then it would say 5,000 requests were processed in this minute, and it would have an average value for latency and an average value for CPU usage and summary statistics like that. But so that's obviously quite coarse-grained data. And kind of limits the fidelity of any simulations or analysis we might do, and we've received quite some feedback on that. So what we've done this time is we've actually released all of the individual requests. And so in our case, it would be 5,000 requests with 5,000 CPU values and 5,000 latencies. And that will obviously enable like quite significantly more granular analysis and more realistic simulations. So yeah, in the event of a cold start, the same happens for a cold start. The name of the pod is logged, the time it took end to end, the time it took to allocate the pod, to load dependencies, to load the code, that's all written down, and we've released that table as well. Yeah, so that's just the data that we're building on here. So now that we've discussed some of this background, we'd briefly like to share some of the insights we think are particularly useful, some things we're actively working on based on this data. So the first direction we're interested in is multi-region trends. And so what we'd like to do is discover some similarities and differences between different clusters in our data and see if we can use those differences and similarities for some improved scheduling decisions. So this is a high-level overview of the sizes of our regions. In total, we analyze about 85 billion requests and about 12 million cold start events, and our data set is about a month long. And so there are 5 regions, and the total size of these regions varies quite significantly. So you can see that here. And if we then plot the cold start time distributions and also the resource usage distributions, we can actually see some pretty significant differences. So for example, even though regions 1 and 3 have almost the same number of requests, their cold start times and resource distributions are quite different. And so what we're hoping is that we can maybe shift some traffic from overcrowded regions to less crowded regions so that we can improve the overall performance of our system. So additionally, if we look at requests per minute for each of these regions, we can see that the peak times of these regions are all different. And this is obviously a side effect of different diurnal patterns in different parts of the world, but yeah, so given these differences and the peak time differences, it presents quite an interesting opportunity to move traffic and potentially improve the capacity of our system. So another interesting finding that we've had is that very different functions are responsible for the number of cold starts, number of running pods, and number of functions. So naively, you could assume that the more popular functions require frequent auto-scaling decisions and so cause most of the cold starts. But actually, we've found that this may not always be the case. So for example, timer-based functions make up less than 10% of running pods, but about 30% of cold starts, and they make up over half of all the functions in our platform. So another example of this is the custom runtime, which basically has the opposite pattern. So it's responsible for 3% of functions, 10% of cold starts, and more than 20% of pods. And so it's useful to keep these asymmetries in mind when you optimize for a particular workload. So if you were to optimize something on a function-by-function basis, that may end up being warped to a significantly disproportionate number of cold starts or running pods. So that's just worth keeping in mind for SLOs and things like that. So if we take the number of running pods that we looked at on the previous slide and we expand it over the 31 days of our data set as a time series, we can see some interesting things. So normally, timer functions are brought up as a significant source of periodicity in serverless systems. But when we plotted this, what we figured out is that actually they're quite constant and they contribute very little to the overall workload. And the real contributors of periodicity and let's say stress in the system are workflows and storage triggers that contribute much more to much more aggressive periodic swings, let's say. So we can also, in this, like we've split it by trigger type, we can also split it by the size of the pods, the number of running pods based on the size of those pods. And so what we can see then is that actually the periodicity of those time series is quite regular and quite predictable. And that's something I'll talk about in more detail later because it leads to some useful pre-warming opportunities. So now that we've discussed quite a bit about which types of functions cause cold starts, I want to talk a bit about what components cause longer cold starts. So here we can see the different cold start components over time, as well as the number of cold starts. And first of all, we can see that the contributions of different components in different regions are quite significantly different. So these are all the components that I mentioned earlier. So that's pod allocation time, scheduling, deploying code, and deploying dependencies, and also the number of cold starts in purple. So we can see that we can illustrate the point quite clearly by looking at the holiday period from day 13 to day 24. So after that holiday, number of cold starts and the cold start time increases significantly as traffic picks up again and users start their workflows and so on. So for example, in region 1, most of the cold start time comes from scheduling and dependencies, and those are the factors that increase significantly after the holiday finishes. While in region 4, most of it comes from pod allocation, and the scheduling actually plays quite a minor role. So we noticed that these different data centers would all benefit from optimizing different parts of our system. So there's no silver bullet, no single bottleneck that we can eliminate and kind of improve our system. So if we zoom into a single region now, region number 2, we can plot the cold start time distribution per language runtime, which you can see here. And so the 4 plots I've added here, they decompose this cold start time into its components. So if you were to add all of these components, you would end up with the cold start time. And so what we can see is that, again, there are different bottlenecks for different runtimes, and they sort of suffer from different components. So the one main example of this is custom and HTTP runtimes that are dominated by pod allocation. And the reason that this happens is because custom runtimes are uploaded by the user, and they cannot be pre-warmed as easily as the default runtimes. And for HTTP, even though it's a default runtime, an HTTP server has to be started, and this is quite a heavyweight process in our system, so that tends to take longer. You can also see for Go runtimes that although pod allocation time is fine there, actually the time to deploy code is the bottleneck there. And there are many other examples of different runtimes kind of being bottlenecked by different parts. So we've discussed now quite a bit about cold starts, how long they take, and where they come from. But if we want to get a more end-to-end picture of the cost of these cold starts, we have to think a bit about the rest of the life cycle, basically. So after a pod is cold started, it would be more efficient if we, especially for a longer cold start time, if the pod would last longer and serve more requests than if it was just killed off after a single request. So in order to define this, we can define pod utility ratio, which is basically the ratio of its useful lifetime to the cold start time. So if this is less than 1, it's quite an inefficient pod, especially for a long cold start. And if it's greater than 1, that's kind of what we're looking for, especially for longer cold start times. So we can plot this as follows. And if we look at the same runtimes that we looked at before, custom and HTTP, we can see that, some of the default so they actually perform better than some of the default runtimes. So even though the cold starts themselves are quite expensive, we find out that we get a significant return on investment because they stick around for longer and they tend to serve more requests. So this just expands our horizons a little bit instead of fixating purely on a single metric of cold starts. So now that we've covered some of these insights from our paper, we want to suggest some further work directions that we think are promising. So multi-region scheduling is one thing we're actively working on. So like I mentioned before, given the distributions of resources and latency, and also the different peak times, we find that it may be beneficial to actually move some of the traffic between regions. Another thing that we've actually implemented and that has worked quite well is forecasting demands for pods based on pod size. And so currently we only use pod size as a configuration for pre-warming, but this is quite an active area of research with us. So there are many other potential directions that we've described in more detail in our paper, and you're more than welcome to read them. But yeah, there's quite a range from, let's say, forecasting call chains of workflows all the way to re-architecting serverless systems to get rid of some of the components that I mentioned. So there's fewer reasons for bottlenecks. So yeah, that's the end of my presentation, and I'd like to thank you all for your attention and leave you with the link to our traces and also the code so you can work with them. Thank you very much.